Hello, my name is Srđan Popić, and I will present you a paper, implementation of a simple domain-specific language for system testing in a V-model development lifecycle. In the introduction, I will lay down what we'll be discussing in the presentation. First, we will talk about V-model. What are the system requirements, what's system testing. After that, we will talk about domain-specific language, how to create it, what are the flavors of it, what are the costs and what are the benefits. At the end, we will lay down the examples of usage domain-specific languages in testing domain. After that, we will show you a solution, small part of the source code, and the result of the testing as well. At the end, we will have a conclusion and further steps. V-model development life cycle actually is developed as an upgrade to the waterfall development life cycle. It has these so-called legs inside of it. One side lead to another side from the top level to the bottom, but along with that, it always plans tests that accord to the phase. So if we focus, for example, on the second phase, which can be system requirement specifications, where the requirements on the system level are created, we will need to plan the testings for these requirements at the same time. So one aspect of the software development, every software development life cycle is one goal is to create better quality software of the better quality, and how to do it is to follow these steps. Every life cycle has its own steps, so the pro for that is every V-model has every model actually of development has how-to steps. Those steps actually minimizes the risks in and during the process. As I said already, V-model plans test upfront and finds the defects in early phases because of that. What are the cons? It's more project-oriented than organizational-oriented, so to say. So it's blind for some resources that are there in organization but not on the project. Also, there are no prototypes as well. But what's more interesting for this paper is that the tests became irrelevant from time to time during the life cycle, which is not a good thing which is not a good thing. There are improvements that actually goes the same direction, so in a way to some kind somehow align tests with the requirements, such as W model, which has actually two V models where this alignment is placed in another V, so to say, legs. And also butterfly model, which focus on the testing design already in early phases, not only on testing the execution, but also on testing design on the early phases. Our goal is to create the domain-specific language that can somehow align system test cases with system requirements. Domain-specific languages. First question is it hard to achieve it? No, the answer is no. And the reason why this creation of the domain-specific language is not so hard to achieve is there are two main reasons. One is that there are lots of tools that are developing the programming languages. Another thing is this concept of meta models, where you are modeling your own system, and it's enough for you to have the expert of your system that can model it and actually raise, with these models, you can raise the level of abstraction to the domain level. So this way, the experts of the domain can talk their language, and this language can be actually domain-specific language. There is a wide range of usage of the domain-specific languages. For example, in consumer electronics, in telecom industry, railway, aerospace, other automotive industry, insurance, and for sure there's in software testing. Mostly those languages are developed in-house with no help of some external experts, but only with its own experts in the house. This shows that the most important part of the creation of the domain-specific language is the knowledge of the expert. So you need to include the expert in creation of the language. You need to use their own words and abstractions, and this is a halfway to creation of the domain-specific language. Another slide on domain-specific languages. DSLs have different flavors. On the representation level, there are textual and graphical DSLs. On technical level, we have internal DSLs as well as the externals. Sometimes internal DSLs are actually considered as a set of libraries or API, not even considered as a domain-specific language, whereas the external DSL is a completely new language. Oldest definition of programming language, the distinction of programming languages by execution, we have compilers and interpreters. Any flavor used will need parsing and lexing of the source code. And in those processes, we will have the syntax check. Parsing and lexing will give us abstract syntax tree as a result. What will be done there? We will get the tokens. We will recognize those tokens from the source code, and we will create a hierarchy of those tokens if they are commands, statements, variables, or whatever. And this will create this hierarchy is actually abstract syntax tree. Here is the difference between compiler and interpreter. Compiler actually uses this AST in order to compile, to generate new source code of the lower programming language. Mostly this will be general purpose language, and then transform it and so on. But on the interpreter side, this AST is directly used as a way to interpret the commands. So this is like a last step. This will bring us faster execution in the case of compiler of the program, and in case of interpreter, we will have a less complex, more maintainable, because we will not need to have these compiling steps and transforming steps and so on and so on. And another thing, if we are creating the source code, another source code out of our source code, we will need to know this another language as well. So it seems that the interpreter is a less easier to develop than compiler. Regarding the costs and benefits, first graph here shows the research of costs in time regarding the domain-specific language. It shows that in the beginning there is additional investment because of the engagement of the domain experts and the experienced developer, but as time pass, the cost is less. The same goes when we are repeating the usage of the domain-specific language. The research shows that after three different applications generated out of the domain-specific language, it pays itself, or at least it gets less costs than by using the general-purpose language. Why is that? Because we have smaller set of the commands, statements, variables, and any kind of phrases in a language. And it's easier to grasp from the point of view of the newcomers. And also there is research that says that even experienced developer perceives it easier and better to use. Apart from that, this seems to be, the domain-specific language seems to be a tool of communication, because different parts of the organization, such as domain experts, developers, business leaders, and financials, can communicate on another level, on the level of the domain-specific language, which is known to all sides of the system. Apart from that, regarding the existing DSLs, there is no DSL that do the system testing in a V model lifecycle, but there are a lot of system testing tools, the DSLs. Common ground for all of them is creation of some kind of building block, basic building block, which is either a test case or scenario. And these building blocks are used in order to test the system. They can be, all of these existing DSLs can be divided into two groups. One group actually does non-functional system testing, such as performance testing or security testing. Those are and another group actually models the system from the beginning in order to test it. This means, this brings with it strong technical knowledge, strong business knowledge, and so on and so on. So this will take time, and at the end, none of them have any kind of connection whatsoever with the requirements. So we needed to create something more simpler and more, so to say, more connected to the requirement. In order to create a domain-specific language, we know, for this purpose, we need to know what we are testing actually. So this is a short slide about the tested application. So the tested application is actually some kind of verification tool that uses some input files in order to create some reports. So that's the case. Behind that, I can say that actually those files are either files that goes into the network elements, such as that contains, for example, routing tables, schedulers, or some firmware software for the devices, network devices. Either those files or files that actually defines the network, that configures it, or describes it. So these kind of files are actually verified by the tools that we are testing, and these files are actually XML files or binary files as well, yes. And the output files are strictly either standard output, standard error, or files that are in XML format. There are lots of tools, so it's not only that there is only one type of checking. There are lots of aspects of checking of one file or many files as well. So there is a set of the executables inside of these tools. So the tool can be executed in various ways. So these are the parts that explains what's inside, what is tested actually. Here is the solution. What we have decided is to develop the domain-specific language that is interpreter, external, and with a textual representation. In fact, it will be XML format of the language, which will give us a more simple approach in developing, since with the XML format we have a creation of the AST, the abstract syntax tree is actually parsing of the XML and relaxing the nodes and attributes of the XML. Actually, XML is the abstract syntax tree. The syntax check is also easier. It's actually validation against the XML schema, which is also easy thing to do. What we got with this solution, as any other DSL, we have test cases as a building blocks. Inside of them, we have IDs used for traceability. So in order to connect it with the requirements, we have severities as an attribute of the test case for quantification. So this way we can quantify the complete report. And we have tasks, different tasks, patchers, executors, parsers, and mappers. Here on the image, we can see how it looks like. First, all patchers will be executed. After that, executors, parsers, and mappers. What patchers does is they actually implement the positive or negative testing strategy, which means that they can change the input files and then we can expect a reaction out of the tool because of these changes in input files. So Patchers actually changes the input files. It can change, Patcher can change XML format, as we said, textual, plain textual format, and binary format. All things that we needed for all formats that are actually input formats of our tested application. Executors actually executes the command that any of these executables that are there in the tool, verification tool. They are blind in a way that they can execute literally anything that it's installed or can be accessed to, executed as well. What's after that, after the executions, we parse the output in order to find critical values, for example, errors that needs to be there because of we changed the input files. And in mappers, we actually map expected value against the values that has been found in parsers. So how the source code looks like. This is one extract of the source code, one test case. This test case is actually connected to the requirement that can be said something like when checking the network with missing port, the system must fail with at least one link failed error, port missing error, and edge failed error. So this is how the requirement looks like, and the test case will actually change the input files in order to have one port missing, and then run the check, and after that check if the report contains the errors that needed to be there. So how it looks like. The test case, the building block is here. Here is the ID that actually is aligned with the requirement. Description name. Here can be also as a severity, but the default value of severity is error. There are various levels of severities. Then we have two patches here. One is format XML. It actually patched this file, network1, and put it in another folder. What it does, it actually removed this port, this node port with this name inside of the switch with this name. Another patch actually just copy paste from one folder to another file without any format changing or patching, whatever. Executor actually go to the path. Then in that path, it executes this command, which will actually check the network against the specification and network description, and whatever is in these files will be reported in the third file. And after that, parser actually read this report file in order to find attribute called check inside of the XPath message error. And every value that is found in that attribute is, so to say, mapped to the failed rule. So maybe there will be 10, 12 different checks. All of them will be mapped to the failed rule. So here we can see that we used XPath in order to find the attribute. This can be achieved here also, but this has been shown easier way to do that for people that don't use XPath. It can be done without XPath. So same thing goes here. This can be done without XPath as well. Also, the parser can parse various attributes, more than one attributes, or nodes, or just check if there is existence of the node or existence of the attribute as well. Different things, and map them to some kind of variable called, in this case, called failed rule. Then mappers use this map of variables in order to check if there is a value link failed one, at least once. This means one occurrence. Same goes for other two things here. And I must say that there is also max occurrence here as an attribute. Default is unbounded value, so it can be as many, but if we can also limit it from the upper side, for example, there must be exactly one. So we will say max occurrence equals 1, if that's the case. The report of the system testing actually is aligned to JUnit reports. This way we can implement these tests into any other tool chain. We can put it, for example, in Jenkins. So we can read it in various ways. What's in there? You can see that there is ID of the requirement, can be extracted and directly connected to the requirement. There are the list of failures with messages. Only failures are here. There can be also passing tests, but the thing is that that way we will have thousands of messages. We cannot cannot see the important one from the less important. Conclusion and further research. We enabled positive and negative testing strategy with this tool. Every requirement can be traced with ID of the test case. Test case stays relevant to the requirement. Tests can be quantified as well. The system is robust because the executor is blind at what it executes, and also patchers and parsers cover a wide range of files there. The language is pretty simple. There is no need to use the XPath and regular expressions. Just use it as just knowledge of the XML is needed. What are the further research or further implementation? Additional spell checking, which means there is possibility that you type the wrong ID of the requirement, which will be noted only after the tests are finished, and then try to connect the requirement with the reports from the testing, which will gives us missing requirement or missing test cases. So we'll try to create some kind of mapping between IDs of test cases and the ID of requirement prior to the execution as a syntax check or spelling check. To do so, we need to define some kind of connection between the tool and the system requirement specification tool application where the requirements lies. And when we have this connection, the tool will first, prior to interpretation, the tool will first check all the IDs from the test cases in the requirement set, and if everything's fine, then executes, iterates actually the test cases, and if something's wrong, then throws an exception error, or syntax error, or whatever. Next step after that, what can be seen when you are reading the requirements is that they are actually written in some kind of rigid English language, mostly English language, yes. This rigid language means that the words are used in only one way, and those words means only one thing. Which leads us to try to automatically create the test cases out of the textual representation of the requirement. So in this case, we could actually create some additional code generator that actually generates the test cases, our source code actually, out of the textual representation of the requirements. So this can be achieved after we make a connection with the system where the requirements lies. So that's it.